In this episode, we will talk about advancing AI agents for knowledge discovery and collaboration. The way we interact with information online, it's just completely changed, hasn't it?
Oh, absolutely. It's night and day compared to the early web.
I mean, think back. It was almost like a small digital library at first. Now it's this enormous, constantly shifting ocean of data.
Yeah, everything from documents, databases, you've got social feeds, knowledge graphs.
Even data from Internet of Things devices pouring in constantly. It's massive.
It really is. And the big question that one we're grappling with is how do you make sense of it all? We've tried different things over the years.
Exactly. We started with, remember Yahoo? Those human-curated directories?
Oh yeah, feels like ancient history now. People actually sorting websites by hand.
Kind of quaint, right? But obviously, as the web just ballooned, that couldn't keep up.
No way. That's when keyword search really took over.
Yeah.
Google, Bing. Type in words, find documents.
Which is still fundamental, obviously. But it's mostly about matching words, isn't it? Finding documents containing those words.
Right, it's not really deep understanding.
And that's what we're aiming for now, isn't it? Moving beyond just finding stuff to systems that can genuinely understand and, I guess, help us solve complex problems using all that information.
And that's where large language models, LLMs, really enter the picture. They have this incredible potential, we think, to go beyond basic retrieval.
To become actual reasoning engines.
Yeah, reasoning engines that can handle this really complex web information ecosystem.
Okay, so let's unpack this. Today, we're diving into how we can basically augment these LLMs, make them even better reasoning tools for this messy online world. And this deep dive, it's based on some really interesting work being explored over at Stanford University. Folks like Jur Leskavec and his collaborators, Shirley Wu and Charles Kanatsoulis.
That's right. And their research, it really highlights that while LLMs are amazing just sort of pointing them at the web as it is,
Really?
well, it throws up some serious challenges.
Okay, like what? What are the main roadblocks?
Well, one of the big ones is factual grounding.
Yeah.
LLMs can sometimes, let's say, drift from the facts.
Right, the infamous hallucinations.
Exactly. So you might ask for product specs, and it just gets them wrong.
Hmm.
Or it misunderstands relationships in a knowledge graph. It essentially, makes things up sometimes.
Which isn't ideal if you're relying on it for accurate information.
Not at all.
Yeah.
Another thing is synthesis. Pulling together information from lots of different places, that's hard for them.
Yeah, I can see that. Real questions often need you to connect dots from, multiple articles or sites.
Precisely. And current LLMs often struggle with that kind of distributed information task.
And then there's the complexity of tasks themselves, right? Things that need multiple steps, maybe even some back and forth.
Yes, like planning a complex trip, comparing reviews, maybe trying to figure out conflicting information online.
Like shopping around or analyzing different viewpoints.
Exactly. That requires a kind of collaborative, multi-step problem solving that isn't necessarily a native strength of these models yet.
Okay, let's make this concrete. Can you give an example of the kind of complex query we're talking about?
Sure. Think about a really specific medical question. Something like, find diseases without known treatments that induce itching in pregnant women.
Wow, okay. Yeah, my standard search engine would probably just throw a bunch of links at me. Maybe some related, some not.
Right. To answer that properly, you need to understand structured data relationships between diseases, symptoms, treatments, maybe in a medical knowledge graph.
Uh-huh.
But you also need to understand the subtleties in medical texts, research papers, clinical notes. It's not just keywords.
It requires linking different pieces of information together.
Multi-hop reasoning, exactly. Plus filtering only pregnant women, only diseases with no known treatments, and then synthesizing it all.
And you're saying current systems often treat, like, text search and knowledge graph search separately?
Yeah, often they're handled by different processes, which makes answering that kind of integrated question really difficult.
Can you contrast that with a simpler query, just to highlight the difference?
Easily.
Yeah.
A much simpler query is like, what are the symptoms of the common cold?
Okay, yeah. Lots of documents have that info pretty clearly stated.
Right. It's mostly retrieval and summarizing readily available information. The medical question, though, that requires a much deeper level of, reasoning across different kinds of knowledge.
Okay, I think I've got a much clearer picture of the problem space now. So this Stanford research, how are they trying to tackle these hurdles? How do you build better AI agents for this?
Well, one really promising direction they're exploring is a framework called Avatar.
Avatar, okay.
Yeah, it stands for Contrastive Reasoning for Optimizing Tool Usage.
Okay. Tool usage. So the idea is to give the LLM tools to work with.
Exactly. Augment the LLM by letting it use external tools like specialized calculators or database query tools or information extractors.
Like giving a chef specific knives and whisks instead of just one blunt instrument.
That's a great analogy. But just having the tools isn't enough, right? You need to know how and when to use them effectively.
Ah, okay. So that's the challenge Avatar is focused on, making sure the LLM uses its tools smartly.
Precisely. Sometimes LLMs struggle. Which tool is right for this part of the problem? When should I use it? How do I interpret what the tool tells me? Avatar uses something called contrastive reasoning to get better at this.
Contrastive reasoning. Let's unpack that a bit. What does that mean in practice?
Think about teaching a student, say, math. You look at the problems they get right, and you look at the ones they get wrong.
Okay.
By comparing those two groups, the successes and the failures, you can figure out why they're struggling. Maybe they're great at addition, but always mess up division.
Right. You identify the specific weak spot by contrasting the good and bad examples.
Exactly that. So Avatar applies a similar logic to AI agents using tools. It has a component called an LLM comparator.
An LLM comparator.
Yes. And its job is to analyze the queries the main agent gets right using its tools and the queries it gets wrong.
Huh.
By comparing those positive and negative examples, the comparator identifies the gap in the agent's tool-using skills. And then this is the clever part. It generates specific instructions.
Instructions for what?
Instructions on how to improve. It tells the main agent how its internal prompts, its own operating instructions, should be updated to use the tools better next time.
Ah, so it's like targeted feedback. You used the wrong tool here, next time try this one. Or you misinterpreted the output here, focus on this aspect.
Exactly. It's a feedback loop for refining tool use.
Yeah.
The whole Avatar process is iterative.
Meaning it repeats.
Yes. The actor agent tries the task, uses tools. The comparator analyzes the good and bad attempts from a batch of queries. It generates improvement instructions. Those instructions update the actor's prompting. Then the actor tries again, hopefully better.
That sounds really smart. A way to learn from mistakes in a very structured way. What kinds of tools were involved in their experiments?
They used a benchmark called STARK. That's S-T-A-R-K, Structured Tool Use Benchmark. It has a whole suite of tools relevant to structured data.
Like what? Can you give some examples?
Sure. There's one called Parse Attribute from Query. Basically pulls details out of the user's question. There's Get Text Embedding, which turns text into numbers representing meaning, so you can compare similarity.
Okay, standard embedding stuff.
Right. Then tools for knowledge graphs, like GetRelationInfo or GetRelationDict to find out about connections between things. GetRelateIdentities finds things linked to a starting point.
Makes sense.
There are similarity calculation tools, like computing embedding similarity, and even tools that use an LLM for checks, like check requirements by LM or get satisfaction score by LM. And finally, a finish tool to give the answer.
That's a pretty comprehensive toolkit. So how did Avatar actually do on this Stark benchmark? Did the contrastive reasoning help?
It certainly seemed to. They compared it against several baselines, things like standard vector similarity search, or VSS, also against agent frameworks like React, which is a simpler step-by-step agent, and Reflection, which is an agent that tries to reflect on past errors, kind of like Avatar, but maybe less structured in its feedback.
Okay, so established methods and the results.
Significant improvements. They measured using hit at 1 primarily.
Hit at 1. That's getting the single correct answer right at the top first try.
Exactly. And across the different Stark data sets, Stark Amazon, Stark Mag, Stark Prime, Avatar, showed really substantial gains over those baselines.
How substantial are we talking?
Okay, so relative improvements in hit at 1 were plus 16.5% on Stark Amazon, plus 8.9% on Stark Mag, and a really big jump, plus 20.7% on Stark Prime.
Wow, those are not trivial increases, especially that last one.
No, definitely not. It shows this method of learning how to use tools really makes a difference in getting the right answer for these complex structured queries. So for you, the listener, this isn't just, a minor tweak. It means a significantly better chance the AI gets precisely what you need right off the bat.
That saves potentially a lot of back and forth or wrong answers. That's really impressive. Was this just for that specific Stark benchmark, or did they test it more broadly?
They tested it more broadly, too, on general question-answering data sets, things like Hotpot QA, ArcCV QA, and a tough part of Tool QA called Tool QA SciRX Hard.
And how did it fare there?
Again, it showed noticeable improvements compared to React and Reflection. Relative gains like plus 13% on Hotpot QA, plus 9% on ArcCV QA, and a really hefty plus 33% on that hard Tool QA set.
Okay, that 33% is huge. It really suggests this contrastive reasoning for tool use is a generally useful technique, not just for one type of task.
That seems to be the takeaway, yes.
Right.
It's a robust way to make these agents better tool users across different kinds of knowledge work.
So better tool use is one key part of the puzzle. But you also mentioned another concept earlier, LLMs as active collaborators. That sounds like a different kind of shift.
It is, yeah. Think about how we usually interact with chatbots or LLMs now. It's mostly passive on their end, right?
Yeah, you ask, they answer. Maybe you ask a follow-up.
Exactly. They're reactive.
Yeah.
But what if your question is a bit vague? Or the task is complicated and needs more discussion? Current models don't really take the initiative. They don't say, could you clarify this? Or have you considered that?
Right. They just kind of wait for you to perfectly formulate everything, even if you're not sure what you need yet.
Precisely. So the idea is to push towards LLMs that are more proactive, that actively collaborate with you. They should seek clarification, engage in more of a dialogue to figure out the best way to help you reach your goal.
And that led to this other framework you mentioned.
Yes, CollabLLM.
CollabLLM. Okay, what's the core idea behind making an LLM more collaborative?
The key insight is about the reward signal used during training. Instead of just rewarding a response based on how good it seems right now, CollabLLM tries to reward responses based on their long-term impact on the entire conversation.
Multi-turn aware reward, I think was the term.
That's the one. Does this response, even if it's just asking a question, ultimately lead to a better final outcome for the whole interaction?
That makes intuitive sense. A quick, seemingly helpful answer now might actually derail the conversation later if it misunderstood something fundamental.
Exactly. So the big challenge is, how do you actually figure out that long-term value, that causal impact of one response on the whole conversation's success?
Right. That sounds tricky to estimate. How does CollabLM do it?
It uses a three-pronged approach. First, something called collaborative simulation. Second, calculating these multi-turn aware rewards. And third, reinforcement fine-tuning using those rewards.
Okay, step by step. Collaborative simulation. What's that?
This is pretty neat. They simulate lots and lots of multi-turn conversations. But instead of needing humans for all of them, they use other LLMs to act as users.
So LLMs pretending to be people?
Kind of, yeah. These user simulators get a task description, maybe a specific persona, like you're a busy student trying to write an essay in the conversation history so far.
Yeah.
Then they generate what that simulated user might say next.
That lets them generate tons of training data for different conversational scenarios.
Clever. Very clever. It allows them to simulate a huge variety of interactions an AI assistant might face.
Okay, so they have these simulated conversations. Now, how do they calculate those multi-turn aware rewards? What makes a conversation good in the long run?
They try to estimate the causal effect of the assistant's response on the final outcome. The final reward for the whole conversation has two parts.
Okay.
There's an extrinsic reward, basically. Did the conversation achieve the user's goal? Did they get the essay draft they wanted? And an intrinsic reward, how was the user experience? Was the conversation efficient? Was the assistant helpful? This might even be judged by another LLM.
So goal achievement plus user satisfaction.
Pretty much. The multi-turn aware reward for a specific assistant response tries to capture how much that single response contributed, positively or negatively, to that final combined reward.
And the third part, reinforcement fine-tuning. That uses these rewards to train the main LLM.
Exactly. Now that they can simulate conversations and calculate these more sophisticated rewards, they can use reinforcement learning, common algorithms like PPO, proximal policy optimization, or DPO, direct preference optimization to fine-tune the assistant LLM.
So it learns over time to make responses that don't just sound good now, but actually lead to better, more collaborative outcomes across the whole interaction.
That's the goal, to make it a better long-term conversational partner.
This sounds like it could really change the feel of interacting with AI assistants. Did they test CollabLM with actual people?
They did. They ran experiments using Amazon Mechanical Turk, MTurk. Over 200 people were asked to do a writing task using either CollabLLM or baseline models.
And what did they find?
The results were pretty positive. CollabLLM led to higher quality final documents. The interaction itself was rated better by the users. And interestingly, people actually spent less time on the task, over 10% less time.
Wow, so better results and more efficient. That's compelling. Did the MTurkers give any, qualitative feedback? What did it feel like to use?
Yes, and that was quite revealing. They mentioned that the baseline models sometimes just agree too easily or asked questions that didn't really help.
Felt a bit passive, maybe?
Yeah, Whereas with CollabLLM, users felt it genuinely helped them navigate the task. It might focus them on one part or even prompt them to think about things they hadn't considered initially.
So it felt more like a real collaborator, guiding the process a bit.
That's the impression, yes. A more active partner in the task.
And was this tested beyond just writing tasks?
It was. They used another benchmark called ABCO-QA. This one specifically tests if a model knows when to ask clarifying questions for ambiguous user input versus when to just give an answer for clear input.
Ah, that's a crucial skill for collaboration. Don't just guess if you're unsure.
Exactly. And CollabLLM did much better here. When the user query was ambiguous, it asked about 3 times more clarifying questions than the baselines.
Making sure it understood properly before proceeding.
Right. And because of that, its accuracy on actually doing the right thing for those ambiguous queries went up significantly.
That really paints a picture of an AI that's less of a passive tool and more of an active, helpful partner. Okay, so we've got better tool use with Avatar, more collaborative dialogue with CollabLLM. The final area you mentioned sounds incredibly ambitious. Automating scientific hypothesis validation.
It is, yes. This is definitely pushing the boundaries. Think about science, the sheer number of possible hypotheses you could generate.
Astronomical.
Right, and the need for real statistical rigor. You can't just accept correlations, you need to avoid false positives. Plus, hypotheses are often stated in natural language, very free form. Automating the testing, that's a huge leap.
So what's the approach here? What's the framework called?
It's called Popper, and its core idea comes from a fundamental principle in science: falsification.
Ah, Karl Popper, the idea that you can't definitively prove a hypothesis true, but you can try to prove it false.
Exactly. So Popper focuses on designing experiments that could potentially disprove the hypothesis.
How does it work? What's the process?
It's an iterative cycle, much like Avatar in a way. First, it proposes a falsification experiment. This means defining the null hypothesis, the baseline idea it's testing against, and the alternative sub-hypotheses, the outcomes that would contradict the null.
Okay, setting up the potential conflict.
Then it checks if this proposed experiment is actually relevant to the main hypothesis being tested.
Makes sense.
After that comes critique. The system examines the proposed experiment. Does it really address causality? Is the data needed likely to be available? Is this experiment just redundant with stuff we already know?
So it's self-critiquing its own experimental design.
Yes. And based on that critique, it reflects and revises the experiment, trying to make it stronger, more likely to yield a decisive result specifically, a falsification if the hypothesis is wrong.
That sounds remarkably like how human scientists operate, proposing, critiquing, refining.
That's the idea. And the researchers note that these kinds of tasks seem well suited to what they call compound AI systems.
Compound AI systems, meaning systems built from multiple parts.
Exactly. Systems that integrate LLMs for understanding the language of hypotheses with specialized tools, like information retrieval systems to find relevant papers, or statistical modeling tools to perform the actual analysis.
Combining the language power of LLMs with the precision of dedicated tools?
Right. But there's a catch. These compound systems, while powerful, can also be somewhat fragile.
Fragile. In what way?
Well, they often involve a chain of steps. Component A produces output, which feeds into component B, and so on. If any one of those intermediate steps goes wrong, if component A produces a flawed result, that error can easily propagate through the whole chain.
The garbage in, garbage out problem, but amplified across multiple stages.
Precisely. A weak link can break the whole chain, leading to an incorrect final conclusion, even if other parts worked perfectly.
That makes sense. It adds points of potential failure.
It does. And optimizing these systems is also really challenging. Many components, like the decision of which tool to use, are non-differentiable.
Meaning you can't use the standard calculus-based methods like gradient descent that underpin a lot of deep learning optimization.
Exactly. Plus, you have different kinds of things to optimize all at once, choosing the right models or tools, writing the best prompts for the LLMs, tuning specific parameters within the tools. It's a complex optimization landscape.
So, huge potential in these compound systems for tasks like scientific reasoning, but still significant hurdles in making them robust and easy to optimize.
That's a fair summary, yes.
Yeah.
And alongside these technical challenges, there are broader questions we need to keep in mind.
Like what?
Things like integrity and reproducibility. If an AI system helps validate a hypothesis, how do we ensure that process is sound and repeatable? How do we build trust?
Crucial for science, absolutely.
And issues of bias and representation, of course. Are the data sources biased? Does the AI introduce its own biases? These are vital considerations as these systems become more capable.
And ultimately, the need for human judgment,
Right.
right?
Absolutely. The final call, especially in high-stakes areas like science or medicine, almost certainly needs to remain human-driven, even with incredibly powerful AI assistants.
So it's really exciting progress towards AI that can genuinely collaborate on complex tasks, moving way beyond just fetching information.
Definitely. We're seeing the potential for AI to become a much more active partner in how we discover, analyze, and work with knowledge.
Which leads to a really interesting final thought for you, our listener. As these AI agents get better at discovery and collaboration, how might that fundamentally change your relationship with information and knowledge in the future? What new possibilities open up? And critically, what role will human insight and oversight play as these systems continue to evolve?
It's a fascinating time and definitely something to ponder. The potential is enormous, but so is the responsibility to develop and deploy these tools thoughtfully.